So hello everyone, my name is Morgan Lynch. I'm a postdoc in the laboratory of Professor Ido Kaminer at the Technion. This work was carried out in collaboration with Eliyahu Cohen and Yaron Haddad. And today I'd like to discuss with you a potential observation of acceleration-induced thermality at a recent high-energy channeling radiation experiment carried out at CERN. And there you have approximately 180 GeV positrons, which are fired into single crystal samples of silicon, where the regular lattice array of the silicon causes the positron to oscillate back and forth regularly, radiating photons. This experiment was designed to measure radiation reaction, and here we see the standard catalog of radiation reaction models compared to the experimental data. And since these systems are highly accelerated, what we wanted to do was to incorporate techniques from quantum field theory and curved spacetime, namely the Unruh effect, into a theoretical description of this data. And so what we were able to derive is this Larmor power spectrum, which incorporates the Unruh effect. And in order to match this to the data, we adopt an acceleration profile based off of radiative energy loss, as well as a suite of best fit parameters to take into account detector efficiencies for the experiment. And our energy gap of our Unruh DeWitt detector is this polynomial that you see down here on the bottom right, where the A0 term encodes the channeling oscillation, and the A2 term should encode the recoil or the radiation reaction. And then from there, we minimize and perform a chi-squared analysis. But first, we note that the system will have to have time to thermalize. And when we look at the emission lifetime, we find that there is a hard cutoff at 22 GeV, below which we are not thermal, above which we have time to thermalize. And we see that the chi-squared rapidly converges to 1 above that thermalization threshold of 22 GeV. So let's look at the 30 GeV cutoff, which is the first where the chi-squared goes to 1. On the right-hand side here, we see that it describes the data with our chi-squared of 1, and we could also change the temperature of the Rindler bath away from the Fouling-Davies Unruh temperature, which are these pink curves here that you see. And we find that the best fit of the temperature is actually the Fouling-Davies Unruh temperature, which we found to be 1.96 peta-electron volts in the lab frame. In the co-moving frame, it's 0.7 electron volts. And in order to bolster this claim of acceleration-induced thermality, we sought corroborating evidence via the Bekenstein-Hawking area entropy law. And so via this Rindler horizon dynamics, which is integrated directly from the data set, we see that it converges, the area to entropy ratio converges to 4 times the Planck area above that same 22 GeV threshold. And so to conclude, what we found was the presence of recoil or radiation reaction based off of the best fit parameter of the omega squared term in our energy gap. We found evidence for the observation of the Unruh effect, both in the measurement, the direct measurement of the Fouling-Davies Unruh temperature, as well as the chi-squared going to 1 above that hard cutoff at 22 GeV. We also found that the Bekenstein-Hawking area entropy law was upheld or was satisfied above that same 22 GeV threshold. And so from that is our body of evidence for a potential observation of acceleration-induced thermality. And I'd like to thank you for your time for listening. Thank you.